So this is the sixth video on index notation. This one focuses on a special sort called scientific notation. So our learning goal here today is that we understand the relationship between standard and scientific notation and are able to change between those two versions, as well as understand how it allows us to represent very large and very small numbers. So scientific notation is a way of writing numbers in terms of powers of 10. It allows us to represent really large numbers or really small numbers in a more concise manner. That means in less digits. So an example of a really large number is, for instance, the mass of Jupiter. So there's Jupiter, and that's its mass in kilograms. You'll see there it has a large number of zeros. And if you were writing that in a number of different calculations, that would take a long time. So what scientific notation does is allow us to write a more compact version. So this is scientific notation. It contains a lot less digits, so 1.9 by 10 to the 27. And that talks about how many places the decimal place has been shifted. So we can go the other way too and look at really small numbers. For instance, the diameter of a red blood cell. And that's very small, it's microscopic. So it has a diameter of 0.000006, which is millionth of a meter. And in scientific notation it can be written as that 6 by 10 to the negative 6, which once again talks about how many places the decimal place has been moved. The negative index indicates that it's a really small number. So we already looked at this previously. As we move up this table here, starting with 10, we're adding 1 to the index each time and we're multiplying by 10, which increases the number of zeros in our number here by shifting the decimal place 1 to the right. So these will look familiar with our scientific notation. These are the bits that go at the end. Similarly, we can go back the other way and look at negative numbers. So this is 0.1, 10 to the negative 2 is 0.01, etc. And that's how scientific notation determines the place of the decimal point. So let's have a look. This is the two things you need to know about scientific notation. Its structure is as follows. Always has a leading number between 1 and 10, and an index of 10 as well. So the first bit, written in green here, is this piece here. So it must be between 1 and 10. If it's not between 1 and 10, it's still a valid number, it's just not in scientific notation. And then we have the red bit here, which is the index with a base of 10. That says how many places to shift it. So 10 to the power of 7 is actually 10 million. It has 7 zeros in that digit, in that number. Now on some calculators you'll have a button that looks like by 10 to the power of. On others you have an E button or an EXP button. And depending which calculator you have, it displays them as one of those two answers. So let's look at how this works. Positive indexes make numbers bigger. Negative indexes make numbers smaller. So here's 723 million. We're going to change that to scientific notation. So the first thing you do is take these three digits here and we write them down. 7.23. So that's the first step, a number between 1 and 10 with the digits that exist. The second step is to add in the base 10, which says how many places we've shifted the decimal place. So let's move on a bit here. In this case it's by 10 to the power of 8. So we've shifted the decimal place from here to here, and that's 1, 2, 3, 4, 5, 6, 7, 8 places, hence the power of 8. Going the other way, 6 by 10 to the 7, what we do is add in the zeros. So we start with our number. The 7 there indicates how many places we've shifted the decimal place the other way. So we start by writing the digits we're given and leave out the decimal place. So this is just 6 in this case. And we move the decimal place to the right, the number of places indicated by that index 7. So there's 1, 2, 3, 4, 5, 6, 7. Okay, and we add in those zeros there. Going the other way, or with the decimal number, same thing applies here. 3.68 by 10 to the 4, start by writing 368. There's our decimal place. And we're going to shift it 4 places, 1, 2, 3, 4 to there, and fill in those gaps with zeros. Okay, so it's actually 36,800. Decimal place moves from there to there. Now this is our negative index one because it's a number. It's a small decimal number. Same process as before. This is 3 by 10 to the negative 8. And the reason is, how many places we move the decimal place? 1, 2, 3, 4, 5, 6, 7, 8. Another example. You may want to pause at this point and have a look at it yourself. We start with the 749. We write that as a number between 1 and 10. So 7.49. And we shift the decimal place 1, 2, 3, 4 places. So it's by 10 to the negative 4. Okay, going the other way. As before, write the digits we know. Now this time we're going to shift it to the left here to make the number a small decimal. We're going to shift it 4 places from here between the 1 and 7. 1, 2, 3, 4. So 1, 2, 3, 4. That's our decimal place there now. And then we fill in the rest with zeros. So 0.00017. The last thing we need to talk about with standard notation or scientific notation at this point is significant figures. That lets us determine how accurate a number is. So digits are classified as significant if they are not zeros in an answer. They are zeros between two other digits. So here, that's our significant figures. And then they have trailing zeros. Now I said this is the hardest one, but it's not really that much harder than the others. This just determines our significance or how accurate our answer really is. So in this case, these 2 zeros here at the end are significant because the number is valid without them, but it shows that we actually did measure it or did work it out to that many decimal places. So as an example, when we measure things with a ruler, we have, for example, 2.78 meters here. This is called 3 significant places. And what it does is indicate that we've measured it to the second decimal place of meters, which in this case is the nearest centimeter. That indicates that our measuring instrument, which might be a meter ruler, is accurate to the nearest centimeter. The second one here has a 0 on the end, so that's 4 significant places. And what that means is that we've measured it now accurately to the nearest millimeter. So significant places are very important, particularly in engineering and science, where we are concerned about how accurate we are. So here's an example with scientific notation in significant figures. So there's 340,000. We're going to convert that to scientific notation with 3 significant figures. So same as before, we write the number between 1 and 10, 3.40, and this time we want 3 digits to make it significant to 3 significant figures. The next step, work out how far we'll shift the decimal place. So in this case, we've moved 1, 2, 3, 4, 5 places. Now let's look at a decimal number, this time to 3 significant figures. Notice there's 4 numbers or digits here. We only want 3 of those. So we write that as a number with 3 significant figures or 3 digits between 1 and 10. So that's 6.7, and that 5 is rounded up by the 9 to 6. And we've shifted the decimal place 1, 2 to there. So it's by 10 to the power of negative 2. So that's the goal today, is that hopefully you'll be able to work out how to change between standard and scientific notation, and also how to work with significant figures.